It turns out that the introduction of mutable state and changing objects has repercussions on object identity. That means the question, when are two objects the same or when are they different? We're going to look at this question in detail in this unit. So previously, the question whether two objects were the same had often a rather easy answer. Let's say we had two value definitions, x equals e and y equals e, where e is an arbitrary expression, and we don't consider any assignment, then it's reasonable to assume that x and y are the same. By that we mean that we could also have written x equals e and y equals x, and that two forms of definitions would mean the same thing. That property is usually called referential transparency. In fact, if we use the substitution model, then having written that, we would reduce in one step to a program like this, because the rule for value references means that we replace a value reference x by its right-hand side e. So we arrive from here to here in one step. But it turns out that once we introduce assignments, the waters are considerably muddied, and we will see how in the next slide. So once we allow for assignments, the two formulations above, here and here, don't mean the same thing anymore. For instance, if we define two bank accounts in x and y, can we reasonably assume that x and y are the same? What do you think? So if you're like me, then I believe the answer to that would be clearly no, because creating two bank accounts should give you two things that are different. But on what grounds precisely do you base that answer? Is there something that tells you clearly that now the answer, if you create two definitions with the same right-hand sides, they give you back something different, whereas before it was always the same? When do you make that decision, in what direction? Well, to respond to that question more precisely, we need a theory of what it means to be the same. And the precise meaning of being the same is defined by a property called operational equivalence. In a somewhat informal way, this property can be stated as follows. Let's say you have two definitions for x and y, and they are operationally equivalent if no possible test can distinguish between them. So let's see what we mean by that. To clarify that, we have to look at what can be a possible test. So to test if x and y are the same, what we can do is essentially put them in a black box that consists of the definition of x and y, and then an arbitrary sequence of instructions that pokes into these two definitions in any way possible. So let's call this sequence of instructions f, and we say f of x and y because it can access both x and the y. So that was one part of the experiment. We create two bank accounts, we do some things with it. What we do is arbitrary. We have the full choice of operations that we can use in the experiment. So then the second half of the experiment is to run the same sequence of operations on our two bank account definitions, but now we are only allowed to access the x. So where previously we would have a sequence that maybe interleaved called x and y, now every access to y will be replaced by exactly the same access but to the object x. If you can observe a difference from that sequence to that sequence, then the expressions x and y are clearly different because, well, it makes a difference whether you access one or the other. That's the meaning of being different. On the other hand, if every possible experiment, every possible pair of sequences produces the same result, then we say that x and y are the same, because there's no way you could distinguish them. They're not different because there is no test that can give a different outcome on the x and y or the x and x on the right-hand side. So that, in a nutshell, is the definition and the theory of operational equivalence. Let's put it to a test in our bank accounts example. So we start with the expressions, let's x be a bank account and y be a bank account. And let's see whether they define values that are the same. Here's our test sequence. We deposit 30 units into X and withdraw 20 units into Y. What do we get? Well, according to our definition of bank accounts, we get 30 currency units in the first line. Actually, there wouldn't be anything printed. It's just 30 currency units. And we get insufficient funds when we withdraw 20 currency units from Y. Why? Because, well, the initial balance of Y was 0 and X and Y are different, so you can't withdraw 20 from an account with a balance of 0. So that was the first half of the experiment. In the second half, we rename every occurrence of Y in the sequence of operations to X. So now we have X deposit 30 and X withdraw 20. And yes, indeed, now the second line would give us a result of 10 rather than an insufficient fund exception. So the final results of both halves of the experiment are different, and that means we can conclude that X and Y are not the same, that they define different objects. On the other hand, if we now define X equals new bank account and Y equals X, then it turns out that no sequence of operations can distinguish between the X and the Y, so they are the same in this case. Now, to prove that two objects are the same in this theory is considerably harder than to prove that they are different, because you have to show that no possible sequence of operations can distinguish between them. So you have to argue about a possibly infinite number of possible experiments. Whereas to prove that two definitions are different, a single counterexample is enough. Now, one thing the discussion so far shows is that our model of computation by substitution has become problematic, in fact, that it cannot be used. Indeed, if we apply the substitution model to our bank account example, then we can always replace the name of a value by the expression that defines it. So, for instance, if we have these two definitions, then by the substitution model, as we have seen, that rewrites in one step to the definitions on the right. So instead of the reference to X here, I take the right-hand side, new bank account. But we have seen that this change, this step from here to here, in fact, leads to a different program. So clearly going from here to here is not a valid step, and that means that the substitution model as a whole stops being valid once we add assignment to a language. It is possible to adapt the substitution model, for instance, by introducing a store that keeps track of all the references, but unfortunately this becomes considerably more complicated. So in the future we will say with some regret goodbye to the substitution model for all code that is not purely functional, and we will fall back on a more operational and sometimes intuitive reasoning instead.